Right now, let's check the volumetric change in gases. So this section is about the gases. There is one for liquids and one for solids. So right now, let's check this one for gases. The difference between this one and the other ones, liquid and solid, is that a gas, it's compressible. Therefore, if you have something like this inside this gas, if you push this thing like this, you are compressing the gas, so meaning that the volume of the gas becomes smaller. So unlike with solid, if you push this ring, if you compress it like that, it will almost remain like that, but even though it's slightly compressible. So it's the same thing with liquid. If you put water here and then try to compress it, this thing won't move inward. It will just remain where it is. So meaning that the water is not compressible, or it's very, very slightly compressible. Right, with gas, it's compressible. If you compress it like that, the volume of that gas will become smaller. So that is the difference between this one, this section, and the previous sections. Right, we've got about 3 laws relevant to this section. Those laws are from the 3 scientists. Okay, the first one is Boyle's law. So Boyle's law did this experiment at constant temperature. So he decided to find the relationship between pressure and volume by keeping the temperature constant. So we found that the volume of a given mass of a gas is inversely proportional to the pressure to which it is subjected to. So is this thing. So he did this experiment, and then by ensuring that the temperature is constant, meaning that the temperature of this gas, he ensured that the temperature of this gas inside remained constant, doesn't change. So what he did, he was trying to find the relationship between this volume. The volume are referring to this space here. So this space here, bit from here to there, is the volume. And then the pressure is when we apply the force over a certain area, then the pressure will result. Right. So let's check here. As I'm applying the pressure from this side, my pressure is not even constant. I have to, for this thing to move inward, I have to keep increasing my pressure. My pressure mustn't be constant, because if I keep my pressure constant, it will stop somehow. So if I want this thing to keep on moving, remember, as I'm pushing this thing, the gas is also resisting, is pushing in opposite direction. Therefore, if I don't increase my pressure, hand pressure, at some point this thing is going to stop. So to get this thing moving, I have to increase the pressure. Therefore, what happened is that you apply a pressure from this side increasingly, and then let's see what's happening. So as I'm applying pressure from the other side, what's happening? What's happening is that the volume of that gas, I'm referring to that space there, that space that contains air between the black thing and this bottom thing there, the space or the volume is becoming smaller. As I'm doing what? As I'm applying pressure from this side, as I'm applying pressure increasingly from this side. Therefore, what we can discover here or conclude here is that the pressure is inversely proportional to the volume. Okay, let's check that thing. The volume is inversely proportional to the pressure. The volume is inversely proportional to the pressure, but the vice versa as well. I hope it applies. So it means that as the pressure becomes big, as you keep on increasing the pressure, what's happening to the volume? The volume becomes smaller. So that's what this guy found out. So make sure that you know that Boyle's law for exam purposes as well. This is the graph for Boyle's law. Then the relationship between the volume and the pressure. Okay, this one is wrong. This one is wrong. So the right one is this red one here. So you can see here, you can start at any point. Okay, from this scenario here, we've started. If we start here, remember at this stage our volume is big, so it's here. And then our pressure is small. So right now I'm applying the pressure, little pressure there. So as I keep on pushing this thing, I'm increasing my pressure. So meaning that the pressure is growing from here maybe to there. The pressure is increased. Remember the pressure is measured from this side. From here to there, the pressure increased from here to there. But at the same time, what's happening to the volume? The volume is becoming smaller. So as I'm going down like this, which is this scenario here, the volume is becoming small. As you can see from here to there, this is the small valve, this is the bigger valve. The volume is becoming smaller and the pressure is becoming big. From here to there, the pressure has grown. But from here to there, the volume became smaller. So that is the graph that represents the Boyle's law. So another law is Charles' law. So Charles' law states that the volume of a given mass of a gas at constant pressure is directly proportional to its thermodynamic temperature, where T is the thermodynamic temperature in Kelvin. So in this case, we're going to keep the pressure constant and see the relationship, observe the relationship between the volume and the temperature. So the relationship between these two, the volume of a gas and the temperature, is that they are directly proportional, meaning that as the temperature increases, the volume will increase provided that you keep the pressure at constant. Right. Myself, I normally used to see this when I burn the rubbish. There normally will be the bottle of whatever, cold drink or whatever, let's say 2 liter for drink. Maybe it's made from plastic material. If you make a fire here or flame next to this thing, so normal what I used to observe is that I will start seeing this bottle expanding. So this bottle will expand, and then after some time it will explode. So it will expand from that and maybe to that size, and then after that it will explode. So what does it tell us? That is that it tells us that as the temperature increases, this gas inside expands. So the particles inside, remember gas is made of particles. So the gas particles, as you change the temperature, heat the temperature, the gas particles start moving fast inside that container. By moving fast, they will start pushing this thing. In that way, the volume of the gas will become big. Okay, but in this scenario, the volume is not constant because the bottle size increased. If the bottle size increases, that means the volume is not constant. So in this scenario, we have to keep, we're keeping the pressure constant in this scenario. Okay, let's start here. If you've got this thing, if you don't allow this thing to move and then you increase the temperature, maybe you put this thing next to the heat or something. As I've said here, the gas will do what? Will expand. So as the gas expands, it means that the pressure will increase. So the pressure will only increase if you don't let this thing to move. So if you keep this thing constant, you don't let this thing to move, then the pressure will increase. But if you don't want the pressure to increase, you want to keep the pressure constant, then you'll have to allow this thing to move. You'll have to allow this thing to move. So in other words, you'll be doing what? As the temperature increases, the pressure of this gas inside will try to expand. But at the same time, simultaneously, as that gas tries to expand, you will increase the volume. By increasing the volume like this, the pressure drops. So it means that two things simultaneously will be happening. So the gas will be trying to expand. In doing that, it will be trying to increase the pressure. But because we don't want the pressure to increase, we drop the pressure of that gas by moving this thing outward. So the combination of these two things, they will result with the pressure not increasing. So in this case, we keep the pressure constant and then we look at the relationship. So as I've said that if you want the pressure to remain constant, then you have to allow this thing to move like this. So now, if you allow this thing to move like this, so what you can observe is that as the temperature changes, this thing will be moving outward. So as this thing moves outward, the space between this and this increases. That space gains volume. It means that the volume increases. Therefore, we can say that as the temperature increases, the volume of this gas increases. So that's why they say that the volume is directly proportional to the temperature. As the temperature increases, the volume increases, provided that we keep the pressure constant. So that is what this guy Charles found after experimenting this thing. Right. This is the graph that illustrates that Charles law, or that represents that Charles law. Yeah, our temperature starts here. Temperature starts from negative 273 degrees Celsius. The starting point of temperature is not zero. Zero is just the freezing point of water. So temperature doesn't start at at 0 degrees. So it starts here, negative 273 degrees. So that's why we have to start our graph here. Then as you can see, this line, as the temperature, as you start here moving upward, what's happening is that your temperature is increasing from negative 273 to 0, from 0 maybe to 100, from 100 to 300. So in that way, the temperature is increasing. At the same time, the volume is increasing as this thing is going up. As you are moving like this, you are going up. So as you are going up, the volume is increasing as well. So this line represents that. So the volume is directly proportional to the temperature. Right. The last one is this one. It's Gay-Lussac's law. So it describes the relationship between the pressure and temperature at constant volume. So this time we keep the volume constant. So I spoke about it. So here is your thing. I spoke about it earlier, that if you increase the temperature, those gas particles will start to expand or move faster. By moving faster, then the pressure will increase. So if you don't let this thing to move, it means that you are keeping the volume constant. If you don't let this thing to move, then as the temperature increases, the pressure in this thing will increase. So that one of this bottle. So the pressure will increase. That's why at some point it's going to burst this thing. So it's the same thing here. If the temperature increases and then you keep the volume constant, that might result with this thing bursting or exploding, because the pressure will increase as the temperature increases. So if you want to avoid that burst, then we have to let this thing to move. We have to let this thing to move, but get the previous law. With the current law, we keep the volume constant. So if you keep the volume constant, what's going to happen is that the pressure will increase as the temperature increases. So that's all. We keep the volume constant. Right. We do have this general formula here. This formula here. P1 V1 over T1 equals to P2 V2 over T2. Right. Let me see from this where they wrote it. Is the combined is this one. So from the first law, if you keep the temperature constant, it means that T1 will be equals to T2. And then if T1 equals to T2, then at the end, you will remain with this part. P1 V1 equals to T1 V2. Then if the question says that the temperature remains constant, then the formula that we'll have to apply is this one. P1 V1 equals to, I can see typing error here, is T2. Let me see from this. Yeah, you will use this. P1 V1 equals to P2 V2 if the temperature remains constant. Right? According to Charles' law, if the pressure is constant, then you will have to use this formula. V1 over T1 equals to V2 over T2. So it's from this here, if the pressure is constant, it means that P1 will be equals to P2. P1 will be equals to P2. Therefore, they will divide each other. Then will remain with V1 over T1, V2 over T2. So, lastly, from that one of Gay-Lussac's law, where we keep the volume constant. So, if we keep the volume constant, it means that V1 equals to V2. Then you will remain with P1 T1 equals to P2 T2 if we keep the volume constant, V1 equals to V2. Right, let's go to the exercises from our textbook. Right, the first one. Ammonia gas occupies a volume, its initial volume. Initially, the volume is that. and then at the pressure of, that is P1, initial pressure, calculate its volume at a pressure of if the temperature remains constant. So now we raise the pressure to this value. So if we raise the pressure to this value, what will be the volume? So we have this thing like that, as I've illustrated from that first law, I think is Boyle's law. Keep the temperature constant, you compress this thing. What's happening is that the volume becomes smaller. We're looking for V2. Therefore, V1 is 1.2. As we pressurize this thing like this, we expect the final volume to be smaller. So get this one here. Then again, at P2, the pressure will have to be big, because as you compress this thing, that gas inside gains the pressure. So that's why P2 will have to be big. Then from there, since the temperature is constant, then this one equals to that, then you'll remain with this. Then you'll just have to substitute and get this. Right, with number 2, air is compressed from, that means pressure 1. They gave you T1 from 20 degrees Celsius. One other thing is that in this section of gases, always, okay, please note, when using the formula, the following gas formula, the temperature value should always be in Kelvin, not in degrees Celsius. So as long as you see yourself using this formula or this one, your temperature must always be in Kelvin, unlike that one of solids that depends on the coefficient of expansion. So always make sure that your temperature is in Kelvin. Right, from this statement, the volume is half of the original volume. Oh, we compress. We have this thing here. We compress this gas until the volume is half of the original volume. This is the original volume. So what's happening here is that we are going to push this thing inward, or compress this gas up until halfway here, up until there. So we are going to compress this thing. Make sure you close here. You compress this thing. As you compress this in, the pressure increases. You compress this thing up until halfway. So this is halfway. Then at halfway we stop. This is the final, our final destination. So at this part, the volume is smaller, as you can see. So this volume equals to what? Equals to half of what? Of the original volume. Originally, the volume was here. Then we compressed this thing up until it reaches here. So in that way, we say that the final volume, which is this one, the final volume equals to half of the original volume. So final volume is what? Is 2. 2 equals to half of the original volume. So from this, mathematically, if you want to make V2 the subject of the formula, you can multiply both sides by 2. Then finally we'll have V1 equals to 2V2. Right. But temperature remains constant. So if temperature remains constant, this one will divide that one, will remain with this. So get this one. So therefore, you'll replace P1 by this, V1. We don't know the numeric value of V1. But what we know is that from here, V1 equals to 2V2. Then you can replace V1 by 2V2. P2 is unknown. You can just write B2. V2 as well, you don't know the numeric value of final volume. You can just write V2. From here, this V2 will divide this one from the other side. Then you will remain with this. Then from here, the only unknown is P2. Then P2 equals to that. Or you can say P1 is this. V1, you don't know it. You can just write V1. P2, you don't know it. Then V2, instead of V2, you can write the final volume equals to half of the original volume. Instead of V2, you can write the V1 over 2, which is half of the original volume. Then from there, what you can do, you can multiply both sides by 2, both sides by 2, these 2 divide this, then it will remain with this. Number B, the final temperature if the air is now heated to original volume at the new pressure. Right. Okay. Yeah, this one was supposed to be B, not 3. This one is B. This one is B. This one is A, this one is B. So what's happening is that we are going to heat the air. We are here now at 2, at stage 2. We've compressed this thing up until to this point. So if you increase the temperature, what's going to happen? The gas will expand. So as the gas expands, it's going to do what? It's going to push this thing. So we're going to allow that gas to push this thing up until it reaches that initial point. Remember, initially we were here and then we compressed it to there. Then here we reach this, and then what we do again is that we increase the temperature of this thing, and then this thing will expand up until it reaches the initial volume. So in this way, this is our final volume. So in this case, they're just trying to tell you that the original volume, which was this initially, equals to the final volume. So this is the final volume according to that statement, this one. We heat this thing until the volume equals to the original volume. So in that case, it tells you that V1 equals to V2. Then if you come to this general equation, combined equation, then V1 equals to V2, you'll remain with these ones. Then you know P1, 100, P2, what is this? Oh, this one is T1. Where is this coming from? T1, T1, T1. Oh, it's from here. So you can just interchange this thing, take this one here, P2, and then take that one to there. Then you will have this. Right, you'll just have to substitute, then you will get here. So what I was saying is that you can take this one to there and then take this one to there. You will have this. So in other words, you can say P1 over P2 equals to T1 over T2. But this unnecessary thing, you can just directly come here and substitute, or here and substitute and solve for T2. Right, the next problem, straightforward as well. What's happening here is that the pressure remains constant. Therefore, if the pressure remains constant, you will come to this formula, pressure remains constant, this one equals to that one, then you will remain with this. Then from here, you just have to substitute. V1, you don't know it, T1 is this one is given. T2 is given as 345, you replace T2 by that. The final volume, okay? What they said here is that the final volume where is that? Okay. The volume increases by 0.3 meter cubed. The volume of the gas at 280 K increases by 0.3 if the temperature increases by. I think I've seen a certain sketch from here. Let me quickly check. Yeah, you can say that you have something like this original. Something like this original. So as you increase the temperature, the volume of this will increase from here to there. Then this part we will call it the change in volume. And then if you want the final volume or the volume after the temperature change, then this is your new volume. Initially the volume was here before we change the temperature. After changing the temperature, as you change the temperature, the volume grows. This is the final volume. So this part will be V1. This one will be V1. And then from here to there will be the change in volume, which is that 0.3. So this total volume will be equals to, this total volume or this final volume, V2 will be equals to V1 plus 0.3. Therefore, in this case, V2 equals to V1 plus V3. So that's why here instead of this V2, you will write V1 plus 0.3. Then from there you will only have one unknown, which is V1, and then you solve V1. The next one, the volume of a gas is 0.5 at pressure and a pressure of 800 kPa. Calculate thermodynamic temperature of the gas if the volume is at the pressure of. Right, from this, they didn't mention that a certain variable is constant. So that means that we are not going to apply Boyle's law, Charles' law, and the Gay-Lussac law. We are not going to apply one of those laws. Nothing is constant here. So if nothing is kept constant, then we are going to apply this formula. Then everything is given there. You'll just have to substitute, and then you will find that the only thing that we don't have is T2. This one is missing a certain information, that number 5 there. We are going to jump it because it might confuse you, but this is how they arrived to the solution. But for us, let's jump it. Let's check number 6. Okay, we have this equation, general and characteristic gas equation is this one. So it says PV equals to mRT. It's this one. PV equals to mRT. Therefore, if you want to calculate the mass of the gas, then you will have to use this formula. Generally, in this section, you will have this formula and this formula generally. Therefore, as you can see from this formula here, there is no mass. So if they ask you to calculate the mass, or if they give you the mass, then you must know that this formula will be applicable. We can use this formula to calculate temperature at a certain condition, or volume at a certain condition, or pressure at a certain condition. Right. Let's check from that exercise, number 6. Mass, 6 grams of oxygen. 6 grams of oxygen gas at a temperature of, that means is what? Is T1, have a volume of V1. Calculate the pressure in the gas if the gas constant for oxygen is 280 joules per kg Kelvin. Right, as I've said that the temperature must be in Kelvin. As you can see, this thing is in K, then the temperature must be in Kelvin as well. That will always be the case. Okay, we've got mass. If you've got mass, we've got the characteristic gas constant, then that automatically tells you the applicable formula for that kind of information will be this. Then from that information, just substitute there. This is V1 is this one, and then M. Remember, standard unit for mass is kg. Then we have to convert this 6 to kg. You divide it by 1000. Is this one. This one is given. This one is R. And then T1 you convert it to Kelvin is this one. Then from there you'll get the pressure at those particular conditions. Right, you can still use this formula to calculate any variable at any condition. MRT1. So you can have this, or you can say P2 V2 equals to MRT2. So if you want a certain variable at the condition after temperature change or after changing the volume, you can use this. Before, at initial stage or before you change the volume or temperature, you can use this. Right, we will meet this thing along the way. Okay, number B, calculate the final volume of the gas if the pressure is tripled. Or if the pressure is tripled and the temperature increases too. Right, if you have something like this, and then you push this thing or you compress it. So what's going to happen is that the volume will become smaller and then the pressure will increase. So what's happening here is that we're going to push this thing up until the pressure becomes three times the initial one. So the final pressure will be three times the initial pressure. Initially the pressure is low. As you compress it, the pressure increases. Therefore, we're going to stop at the point where the pressure is 3 times the initial one. So that's why you can even hear that sound. They tells you that the pressure now is increased. It's no longer the same as the initial, the pressure there. So due to that statement, then we're going to say that the final pressure will be 3 times P1. So T2 will be that 130. We convert it to Kelvin is this one. Then in that way, from this, they are looking for the final volume. So as I've said that you can still use this formula. You are looking for this. Then you have P2. You have R. R is constant, is for gas. I mean, if it's air, then this value will remain the same. Okay, T2 you have, then we're looking for this. Okay, mass. Mass depends. Mass before and mass after, it depends. Right. Remember, gas consists of the particles. So if you can have a look here. So these are These are the particles. So gases consist of these things, the particles. Right. So the gas has a mass. So gas has a mass. That's why we do have this M here. Gas equation, then we have M. That shows that gas has the mass since it's a matter. So that mass is due to these particles here. Right. What I wrote here is that if you have the container, okay, if there is no leakage, M1 will be equals to M2. If there is leakage, M1 won't be the same as M2. Okay, if you've got, let's see, maybe this container here. What's happening here? Are we compressing or we are just changing the temperature? We are just changing the temperature. Okay, let's assume that this one is still a gas. Let's erase this thing, assume that this thing is gas, erase this liquid, write the gas. So the difference here is that this one is at the lower temperature, this one is at the high temperature. As the temperature increases, this thing will start to move away from each other. From here, they will go like this, gas particles. So before the temperature change and after temperature change. So as long as one of these particles or some of these particles, as long as they don't come out of this cylinder, then it means that the weight of this gas before temperature change and after temperature change will remain the same. So the only time where this mass, the mass of these gas particles will not be the same as these ones after temperature change is when there is leakage, meaning that if you allow some particles to come out of this container, then the weight of that gas will no longer be the same as this one. The weight will be less. So that's why I have this thing. If the particles doesn't come out, then mass 1 will be equals to mass 2. If the particles escapes or leaks, then mass 1 won't be the same as mass 2. So in this case, they didn't tell us about any leakage. So if there is no leakage or escapement of those particles, then M1 will be equals to M2. Then you will come to this, substitute. Remember P2, we're going to replace P2 by 3 times P1. This one is 358 is P1, is from this. We spoke about this thing. And then V2 is unknown. M, you will use the same mass since there is no leakage. Then M1 will be equals to M2. This one, since ele moya, then this value remains the same. Gas, air, that value remains the same. And then this one is T2. Right, from there you calculate V2. The next one, it's straightforward. Maybe due to time, not to make our lessons long, there is enough. But let's check it. Let's quickly check it. They say gas is compressed in a cylinder from a pressure of P1, this one, and a temperature of is T1, is this one, until the volume is 1/4. Until the volume is 1/4. Therefore, we're going to compress this thing from here up to the quarter. This is half up to somewhere there, quarter. Then that means that your final volume, this thing, the V2 equals to quarter of what? Of the original volume. So with this one, V2 equals to quarter of the original volume. So since that the temperature is kept constant, then you will have this. Then you just have to substitute. Then after that, you get P2. Then at the B, the volume remains constant. If the volume remains constant, you will use this. Then remember what they said is that the temperature, if the gas is heated until it's double, until the pressure is double, meaning that P2 is 2 times P1. We are going to the temperature if the gas is heated until, we are going to heat that gas until the pressure is 2 times the original pressure. So that's why we have here P2 equals to 2 times P1. So from here, you just have to come to this. Since the volume is constant, then you will replace P2, this one, P2 by 2 P1. Remember this thing is from here, P1 V1 over T1 equals to P2 V2 over T2. So volume constant, this one divide this, then you will remain with P1 T1 P2 P2. You can interchange them, you will have this, but you can simply substitute directly from here, you will get the same answer. Right, with this one, number 8. Container is a capacity of, that is your V1. That is your volume. Filled with oxygen. Okay, the gas is oxygen at the pressure of 420 P1. P1 there. The temperature is 50, is T1. Later, the pressure drops to is P2. Due to leak, right, there is leak this time. So rather some particles will come out of that container. So if the particles comes out of that container, what does it mean? As I've discussed before, is that mass 1 won't be the same as mass 2. Right, this M1 won't be the same as this one. Since there is what? Since there is a leak. So some particles will come out of that container. In that way, the mass won't be the same. Right, question 1. Calculate the mass. We've got everything. We've got P1, V1. And then we've got everything. Just have to substitute. So this condition is before the leakage. Before leakage, mass will be this. Then now there is leakage. Then what will be the mass of that gas inside that container after leakage? So due to leakage, the pressure will drop to 300, and then the temperature as well will drop to this. What will be the mass? Then you come to this formula, and then you just have to substitute it. Then the new mass, after some particles went out, the new mass will be this. Right. We have to be careful here. Check this. V1 V2, V1. They are the same. So we've got different scenarios here. So if this one, we're not going to compress anything. So when you compress this thing like this, the volume will be changed. But in this case, we have something like this. We are not going to compress anything. What we are going to do is that we are going to open here. As you open here, there will be what? The leakage. Certain particles of that gas inside will come out. But the volume of this container will remain the same. Or the volume of the gas inside this container will remain the same. The only difference is that the pressure will drop. So this thing inside, if you have the gas like this, okay, let me say I compress this thing, the pressure increases to a certain value. At this point, the pressure is high. But when I open here, the pressure drops. But what remains is that the pressure initially, when the pressure was high, before I open here, the volume was this size. But even now, after opening, the volume still remains the same. So in this case, V1 before leakage and after leakage, this space remains the same. In that case, V1 equals to V2. So you have this thing at a certain pressure, then that is initial stage. What's happening is that you open here. So as you open here, certain gas particles will come out, but the volume of this bottle will still remain the same. Then even the gas that will be inside, volume of that gas will remain the same. That gas inside will still occupy all that space before leakage or after leakage will be occupied by the gas. So if you compress this thing up to there, right now I stop there, the gas is compressed. So that space there is filled by the gas. So even after leakage, the gas is still there. This space is filled by the gas. So the volume of that gas remains constant. While the pressure is high, and then after the drop or after opening here, the particles come out, the pressure still remains the same. So that's why the volume 1 equals to volume 2 here. Since we are not compressing anything, we are not compressing the gas, we are just opening here for that gas to come out. So that's why V1 equals to V2. So this one is the mass after leakage, mass before leakage, mass after leakage. So the question is looking for the leaked amount. So if you want to know the leaked amount, you'll just have to take the original mass minus what? Minus the remaining mass. Then if you take this one minus this one, then you will get the mass of particles that went out of that container. Right, I think we've covered almost everything. The rest, they'll just keep on repeating, like this number 9 here. With number 9, they didn't mention that the certain variable volume or pressure or temperature is constant. If they don't mention that, then we'll have to use this. Then on number B, they said that the temperature is kept constant. If the temperature is constant, then use this. Then straightforward. This number 10 as well, nothing new. We've discussed this thing before. To save time, we can jump it. Then let's check the other problems. Right, with number 11, this one, nothing is constant there. So So they gave you this. Okay, what's happening here? A bubble at the bottom of the lake. From hydraulics, the pressure depends at the depth. Depends with the depth. So if you put something I don't know what this lake, but let's say the dam like this, we have a bubble here. So here's your depth. So the pressure of this bubble will depend on this depth. So the pressure of this bubble here won't be the same as this, won't be the same as this. So because of this depth here. So pressure, if I'm not mistaken, it's rho GH, density multiplied by gravitational acceleration multiplied by depth. Right. So since this bubble is at the bottom, right here at the bottom, then we expect this bubble to experience the higher pressure of 450 kPa. So as this bubble goes up to this level where we have atmospheric pressure of 101.3, okay, as this bubble goes up, its pressure becomes smaller. So that's why at this point the pressure becomes smaller. So get this value. Then at the same time, as if you've got the gas, remember, is compressible. Remember at the bottom, the bubble, we've got that bubble. At the bottom, the pressure is high. So if the pressure is high, what's happening is that the bubble will be compressed. It will have smaller volume. So as it goes up, then the pressure drops. So as the pressure drops, what's happening is that the volume of that thing starts to increase. So if you block this thing here, if you compress it and then you block it here, when you release your hand from this side, this thing will go back due to what? Due to that compressed gas. This compressed gas inside will push this thing backward. So as the pressure drops, the volume increases. So expect the volume of this bubble to become bigger at this point. So that's why after calculating V2, your V2 will be bigger than the V1 due to the less pressure there. So nothing is kept constant there. Then you use that general equation. Then the temperature normally at the bottom will be cold, and then at the higher level or at the top surface the temperature will be warmer. So that's why even that bubble will have to grow, because those particles will expand as the temperature is becoming bigger. The last one, a constant volume of a gas at, so get T1 equals to 20 plus 273, and its pressure is 105 kPa, P1. If the temperature is changed to standard, okay, standard temperature is 273, standard pressure is 101. So standard temperature, they don't have to tell you. If they say standard temperature, you must know the temperature is 273. Right, where's that thing? Yeah, it's here. Standard pressure is this one, standard temperature is 273. So we change the temperature to standard temperature. Then from there, you have to calculate what? You have to calculate the new pressure, P2. So if the volume is constant, you will have this. Then we just have to calculate what? P2. Thank you.